which is a Coulomb electric field, at a certain position is given by a charge or a combination of charges depending on what the situation is. But last time we introduced a new electric field which was a non-Coulomb E field, which can be produced not due to charges but rather due to magnetic field, but not just magnetic field, only changing magnetic field. So, and how do you do it? So you have the field which you produce this field is always circular, and if it is circular you can always define a line integral for that. By line integral you mean you can multiply it by displacement, and if the displacement is in a circle, the electric field is also in a circle. And this thing is equal to the change in the magnetic flux, or this is equal to the change in over a surface S. So you have a path here and you have a surface here. So this surface is the area enclosed by that path. So I would kind of go into the detail of this, but this is what we introduced last time. That you have those two sort of electric fields which you can form. One is a Coulomb electric field given by charges, and another is a non-Coulombic field which is given by changing magnetic fields. This one can also equal to an EMF. So if you have an electric field which is produced, it can also drive currents, and if it can drive currents, we can say that it also produces an EMF as well, and that EMF is equal to that thing. So let's try to recap what we did last time, and just to explain what do I mean by all this. So what we had was a solenoid. So if I want to make a magnetic field which is kind of uniform, then what I need is a solenoid, and I can induce a certain current into it by connecting it to a battery and a resistor. So I might have some current here which I would call as I1, and that current is a time dependent current, so I might have a voltage source which is variable. If I change the voltage source and I have a certain resistance R1, I can drive different currents along the circuit just by changing the voltage. Make sense? So if you have currents running around this solenoid, and those currents would produce a magnetic field inside depending on the direction of the current, the current. So if the direction of the current is something like this, so it's going like this. So if it's going like this, so by the right hand rule, the magnetic field which you will produce would be in that direction. So what you would have is a magnetic field which would be almost uniform inside the solenoid, and it can slightly expand as it goes out of the solenoid. And that magnetic field I can assume is more or less constant if current is constant, but if current is a function of time, this magnetic field is also a function of time, and it would change with time. So that's one current loop I have. So if I look at this structure from this side, what I see is a current which is moving in that direction. So if I draw the cross-sectional fault, what I see is a current which is running around in this direction. So the magnetic field is towards me or out of the board. So the magnetic field lines, they would be coming out. So I'm assuming that the solenoid is infinitely long or long enough. Then the magnetic field is given by, which is this magnetic field, V mu naught n I, and because I is a function of time, I can write that the magnetic field is also a function of time, where n is the number of loops in the solenoid per unit length. So if the length of the whole solenoid is d and n are the total number of loops, then the small n is given by the total number of loops divided by the total length of the solenoid. So it depends really on how dense those coils are, and the higher the field would be. So let's try to find out, if you have a magnetic field which is time dependent, what would be the magnitude of the non-Coulombic electric field in this case. So let's try to find out what that field is. So let me clear up some area here. So let's say I want to find that non-Coulombic electric field at a point here, which is point whatever, let's say point Q, and I want to find the non-Coulombic electric field there. So what I have to do, I have to establish a line integral. The question is, what would be the suitable path to establish this line integral? And the answer is easy because of the symmetry. You can always define a path which is spherically, centrally, a circle around the solenoid. So if that point I write here, that's the point Q, then the circle would make a loop around that solenoid. So, and I want to find the non-Coulombic electric field on this path. So I can assume that this might be constant all over that path just by the symmetry of the problem. So that's something which I can assume. So let's write this. So what would be the direction of the path? That's something which we discussed last time. The direction of the electric field which would be produced here. And that, by that I mean the non-Coulombic electric field. So it's given by the dB integral, but rather by the minus of the dB integral, because you have a minus over there and a minus over there and a dV by dt on the right hand side. So the direction of the non-Coulombic force would be given by this direction of minus dV by dt. So if the current which is flowing inside here, let's assume this is increasing with time. So what I have is a situation like this, that I have a current which is a function of time, and that current is increasing linearly with time. So the magnetic field which is coming out, it is increasing with time, and dV by dt has a direction outward of the board, because that's where the B field is increasing along. But so what would be the direction of minus dV by dt? It would be into the board, and if it is into the board, then I can write by right hand rule, if your thumb give you the direction of the minus dV by dt, the fingers would give you the direction of the non-Coulombic electric field. So the non-Coulombic electric field is in the clockwise direction. So if I intuitively write the field vectors, it should look something like this. So these are the non-Coulombic electric field vectors which I have drawn along this circle. but you have to do a path integral. So you can define your path. Let's say you can do an integral along this circle. So at each point, the ds, which is the path elements, it is always parallel to this electric field as well. So, and moreover, what you can assume by symmetry is the magnitude of this non-Coulombic electric field is constant all over just by the symmetry of the problem. So E dot ds, and of course this is the non-Coulombic field on the left hand side. Here it becomes, because E and ds are always parallel, you can simply write E and C multiplied by ds for this closed path P. Makes sense? And so further I can assume that E and C is constant all over this path, so I can take this out of this integral because it shouldn't depend on this. So I can have E and C, and what I would be left is just the integral of the distance along the closed path. True? So let's say if the distance from the center of the closed path is r, then what would be that integral? It would be just the circumference of that circle, and that would be 2 pi r. So that's, I've taken care of the left hand side. Now I have to take care of the right hand side and find out what the right hand side is. So what does the right hand side has? It doesn't have a line integral along the path. It does have a surface integral, and that surface integral is for a closed surface, not an open surface, not a closed surface, because there is no circle over here. So it should be maybe a sheet of, a plane of surface. So what would be that plane of surface in this case? So you have a path, which is this path. So I can write this P is basically this path. Then the surface which I am assuming on the right hand side should be the surface which is enclosed by this whole path, and that would be basically your whole depth. Just this flat plane which is confined in this path P. Make sense? So what would be the area integral? The area integral, you can take an area integral, let's say depending on the direction, the area direction, you can take basically, if you take the E and C direction. So the E and C direction is this one, the area would be in that direction. So what you would have is B dot dA, which is for the surface, it would have, what is B dot dA? That would be simply B dA with a minus sign, because B is outward and A is inward. So that's the E and C. A is inward, B is outward. It doesn't matter that much, because at the end what this minus means, it gives you the direction of the E and C, which you can already find from the lenses law, which I already said. If you know the direction of minus dBt, this should also give you, already give you. So what's important is what's the magnitude of this EC, so you can basically ignore the sign. The direction you can already find from the direction of minus dB by dt. So even if you get confused in the directions there, the easy thing is go to the lenses law and find the direction of the non-Coulombic field from there. Yes. So I just assume that if I use the right hand rule, so if E and C is in that direction, I can say that the area is in the opposite direction. But it doesn't matter at the end. What matters is d minus dB by dt की direction क्या है, because that would give you the direction of the non-Coulombic electric field. what I'm interested in is the magnitude क्या है यहाँ पे. So whatever the sign may be, you have a minus there, and a minus there, come up with d by dt. What is the magnetic field inside? So as I said, it is set by the current, which is a time dependent current. So that magnetic field would be U naught and I of t and dA integral over this whole surface. So what I have on the left hand side is the ENC into 2 pi r, and on the right hand side what I have is d by dt mu naught, or I can take mu naught and out of the integral and d by dt of I of t and dA over the surface S. So because I of t, it doesn't depend on the area, so I can take this out of the integral, so that's what I would have. So what is this thing? This is the total area enclosed by the surface S. And what is that thing? Mu naught n d I by dt multiplied by the area, and then area is pi r squared. So that's your surface. The total area of this surface is pi r squared. Yes. That's true. That's true. So what do you have is, you have only a magnetic field which is in here. So if you take a dot product of this magnetic field with the whole area, what would you get? If you take a dot product here, you would get a 0 because there is no magnetic field. But if you take a dot product here, you would get some value. So what you would get as a function of this b dot dA integral is, तो एरिया यहाँ पे आएगा, that would be the area जहाँ पे आपके पास magnetic field जो है वो non-zero है, and that's the only area which is covered by the solenoid. So that, let's say your diameter has solenoid का, that's A, so you can say that this is equal to pi A squared rather than pi R squared. Sorry about that. क्योंकि what do you have here integral के अंदर? You have b dot dA, so you have to take this integral over the whole surface. So you take b dot dA at each point of the surface. So you have, if you take it here, 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 inside here you would get non-zero value, but outside here you would get zero value. So b dot dA will area आएगा आपके पास, that would not be the total area, but rather only the area where magnetic field is. So that would be, so what would be your non-Coulombic field? It would be given by, we have pi there, that would be mu naught and A squared 1 over R and di by dt. That would be the magnitude of the non-Coulombic force, and you already know what is the direction of this non-Coulombic force. It is in that direction. So what does it tell you? That if you increase, if you move this side, this point Q away from the center, what would happen to the magnitude of this electric field? It would drop because you have a 1 over R dependence. So if I have a loop let's say a point Q is somewhere here, and I have this path rather than this path. So the non-Coulombic electric field है, इसका जो magnitude होएगा, that would be half of what you have there. So it would be and so on. So what I have done is, so that's I have chosen a path which has twice the distance away from the solenoid. Any question here? What about if I have this point Q not outside but inside here? Would there be any non-Coulombic electric field inside a solenoid? So the path which I now take is this one then. And then the distance R is smaller than the radius of the solenoid A. What would happen along this? You would still have magnetic field in that direction, and you have an area now. The area, this would be your path P, and the area would be the area enclosed by this path. And now you have to take the whole area, because inside this area you have a magnetic field everywhere. So integral के अंदर जो area आएगा आपका, that would be a total area enclosed by this path P. So this would be your path P, your new path P, and this would be the surface S over which you have to integrate. So left hand side, what you would get is the non-Coulombic electric field multiplied by 2 pi r. On the right hand side, what you would get is mu naught n di by dt multiplied by the surface integral, and in this case the surface area is pi r squared rather than pi a squared. So you can write this as equal to mu naught n di by dt of pi, would pi be there? Pi cancel out. So pi there, you would have mu naught n into r di by dt. That would be the Coulomb electric field magnitude, non-Coulombic electric field magnitude inside the solenoid. What would be the direction of this non-Coulombic electric field inside? It would be again given by the same direction. So you have to use the Lenz's law, which is choose the direction of minus dy by dt, and it's still the same direction, so it doesn't change. टू है कहाँ पे? हाँ, this ठीक है. This में भी है टू. हाँ, टू रहते हैं. So if I combine both the results, let's say this is distance r, and this is the magnitude of the non-Coulombic electric field, and this is the position, this is the boundary of the solenoid. What you have is, so as you go, so in the center you don't have any non-Coulombic electric field, but as you move away from the center of the solenoid, the non-Coulombic electric field magnitude increases linearly with distance. And if you go out, it would drop with 1 over r, so you have r dependence here and 1 over r dependence here. So what do we mean by this is, let's say if this is your solenoid with a certain radius a, then if you have non-Coulombic field here, you have, so you can choose a path here and a path here inside the solenoid. You would have a small non-Coulombic field But here you would have a large non-Coulombic field. If you go out at this point, you can draw another circle. You would have a large non-Coulombic field. And if you move away, this non-Coulombic field, it decreases in magnitude. So there's the whole picture of it. How does the magnitude of this non-Coulombic field varies inside the solenoid and outside the solenoid. So last time we said that if you have this non-Coulombic electric field, what if I put another coil or a wire around this solenoid? So you have a metal conductor which is at a certain distance r around the solenoid. So what you would have is a non-Coulombic electric field established inside that metal conductor. And whenever you have an electric field inside a metal conductor, you have currents. And what would be the magnitude of that current? It would be given by the EMF, which is because the changing magnetic field is producing an electric field, and that electric field is causing a current. And whenever something causes a current, we say that there is an electromagnetic EMF source within that circuit, and that circuit would draw some current into here, and that current would be given by the EMF and the resistors of that wire. So in general I can say, so what would be the EMF magnitude? Which would be produced along this wire. So let's say this radius of the wire from the center is R. Then the EMF is given by basically that thing. So which is path P and C dot ds along this external conductor. So that's what I have. So, but the good thing now is that I already know what E and C is at that position. And what is E and C at that position? That is mu naught n by 2 1 over r क्या था a squared by r a squared. What is 2 pi r? What is ds over the path p? This is 2 pi r. So the EMF which is produced over that r is 2 pi mu naught n a squared by 2. That's the EMF into di by dt. That's the EMF which you would produce by the changing current. But this current, so that's the current I1 which I am talking about here. So the current which you are introducing into your solenoid, and that's the current dI1. But if you have an electric field here, you can induce another current here, and that current would be due to this non-Coulombic electric field. So if I take this as it is connected to a certain resistor R, this wire, then the current which would flow because of this whole configuration is I2. So you have a current which is flowing inside the solenoid. That current is I1, and that current is a function of time. But then you have another current which you produced as a result of that EMF which you are creating around that solenoid, and that would be another current. And that current would depend on what di by dt is. If di by dt is constant in time, then you would have a current here which would be constant. But if di by dt is again changing, then you would have a changing current again. So what's the case here? This is I1 as a function of time. It has a constant slope. If it is a constant slope, di by dt जो है वो आपके पास that's constant, and if that's constant, I2 का जो magnitude होएगा वो भी आपके पास constant होएगा. And what would be the I2 magnitude? The I2 magnitude would be the EMF which you have produced as a result of the changing magnetic field divided by the resistance within that second coil, which is around the solenoid. And so this I2 would be equal to 2 pi mu naught and A squared. 2 pi मैंने क्यों लिखा था इधर? That's true. Okay. By 2 R di1 by dt. So one change in current is producing another current in another coil. Yes? No, what I said was if di1 by dt is constant, then I2 would be constant. That's what I said. So you have this solenoid, and around this solenoid you have another coil, and you are producing current in that coil which would be I2, and it would depend on how the current inside the solenoid is changing. So what do you have here is the changing magnetic field produces electric field which causes or which induces EMF. So that whole process is called as an induction process. What do we mean by this? That you have current in one direction and it is inducing current in another circuit which is around that. So this process is a so-called an induction process, that you are inducing current in another circuit via any change in one circuit. So, but important thing is that you should have a changing magnetic field, and I don't need a solenoid to create an induced current. For example, I can take another scenario, something like if I have a bar magnet with a north pole and a south pole, and I have a coil close to it, then it would have magnetic field lines coming out of it. So this would be the magnetic field of such a bar magnet. So you have a certain magnetic moment of the bar magnet, and we know how to find the magnetic moment of a bar magnet experimentally. It's not easy to find it theoretically, but you can find it in experimentally. What's the magnetic moment? And if you know the magnetic moment, you can find the magnetic field at a certain distance d along the axis of the dipole. And what would be that magnetic field? that is approximately given by mu naught by 4 pi 2 mu by, let's say this distance is z, so you have a z cube. So this is equal to 2 by 4 pi. Okay, this is. So if you know the mu of such a bar magnet, you can find what the magnetic field here is. And once you know what the magnetic field is, you would know what the magnetic flux through this thing is. And what would be that magnetic flux? That would be given by this B dot TA around the surface, and that surface would be the surface enclosed by this coil. So this coil would be my path, and the surface which is enclosed by it would be the surface S, over which I have to find this.
So what is the distance equal to?
This is just the distance between the bar magnet and the coil. So if I want to find the magnetic field due to a bar magnet which has a certain magnetic moment along its axis, so it's given by this expression which we have find out.
From the center of the bar or the edge?
It's the center of the bar magnet, not the edge. So there would be a magnetic flux through this surface, and I can assume, let's assume that this coil is very small, so the magnetic field lines are more or less parallel, so you can assume that this would make this integral rather easy to solve. I won't solve it, but just imagine this is constant, so you can find the flux through that closed loop. The question is, this won't give you any current, because you won't have any non-Coulombic force, non-Coulombic electric field formed within the wire if this thing is stationary with respect to that. You would only produce a non-Coulombic force if on the right hand side you have a changing flux, not a constant flux. So what you need is a changing flux which should change with time, not a flux which is constant with time. So this has to change with time. It should have a certain d by dt. This is your flux, or the magnetic flux. So what you have to do to induce currents into such a circuit, you have to move the whole bar magnet either towards it or away from it. So that would be one way of changing a magnetic flux through a certain coil, and you can induce a current given by the motion. So what would be the direction of this current if I move the bar magnet towards it? What is happening to the magnetic flux through the bar magnet? It is increasing. So if it is increasing, so I have a magnetic field which is in that direction, and that magnetic field is increasing. So if it is increasing, it means dB by dt क्या direction है? It's the same direction which is this one. So what would be the minus dB by dt direction? It would be that direction. So the current induced होगा, that would be the direction of the thumb, which is in that direction, and the E and C would be produced in there. So जो आपका तो माइनस dP by dt की ये डायरेक्शन है, तो जो नॉन कूलम्बिक इलेक्ट्रिक फील्ड होएगा वो इस डायरेक्शन में होगा, which is given by the finger. So if I look from this hand side, from this side, so what I see is you have that the non coulombic field has produced in that direction, which would draw a current in the same direction. So if you have a current in this way, so this has a north pole and a south pole. If you have a current carrying loop, it is also a magnet. And it's a magnet in such a way that this side would be its north pole and this side would be its south pole. What would happen at this position? you have two north poles facing each other and they would try to repel. What if I try to move this away from it? What if I try to move this magnet away from it? The direction of the magnetic field won't change, but its magnitude through this loop would decrease because I'm moving away from this. So you have B की direction ये है, but dB by dt की direction क्या है आपके पास? It's this direction because you are decreasing the magnetic field in that direction. So the dB by dt की ये direction है, minus dB by dt की क्या direction होगी? It's that direction. So in that case, by the right hand rule, if that's the direction of the minus dB by dt, आपके पास जो current induce होएगा वो up इस direction में होगा, which would be so in that case, if you have current in that direction, so you would have this as a south pole and this as a north pole. They would attract each other. Is there confusion about direction of them? So always first find the direction of minus dB by dt. That would take the thumb as the direction of minus dB by dt, and the finger would give you the direction of the non-Coulombic electric field, and that would also be the direction of the induced current as well. In which case? So when you move away, B field is still in the same direction, लेकिन B field का magnitude क्या हो रहा है? It's decreasing. So if it's decreasing, dB by dt की direction क्या है? It's not in the direction of B, it's rather opposite to it. So minus dB by dt की क्या direction होगी? That would be that direction. So you would have a current now moving in that direction rather than this direction जो कि पहले हो रहा था. Okay. You don't need also what's important is that you should have a changing magnetic field, which you can also have is, for example, if you have a coil you have a coil, the coil is also, it acts as a magnet. So if you have a certain current running around in a certain direction, it would have a certain magnetic field. Let's say that magnetic field, it is like this, so the magnetic field की direction क्या आपके पास होगी इसकी वजह से? That would be into the pole. Again you bring this coil, this other coil close to it. So this is coil 1, which has this, and this is coil 2, which is close to it, and it has a certain resistance connected to it, which is R2, this is resistance R1. So for example, if you can, so you have this magnetic field B which is produced here, and that magnetic field is dependent on the current which is flowing in that loop. So you provide a certain voltage, you have a certain resistance connected in series, and you have a certain current which will flow to it. But if this current is a function of time, the magnetic field is also a function of time. So what you would have is the magnetic field it would be changing with time. So because of this magnetic field, some of these magnetic field lines would pass through this coil as well. So you would have a magnetic flux through that coil. So that magnetic flux, which is B dot dA through this path P, through this surface S, which is enclosed by this path P, that would be also a function of time because B is a function of time as well. So what would happen here, because the flux would be changing with time, you have d phi m by dt, which is a function of time, and you would have an EMF created in that coil, which would cause a current in a certain direction. Sorry? अगर resistor नहीं लगा हुआ, then the current will be infinite, and you don't want an infinite current. That's what short circuits are. You don't want short circuits. So, but the important thing here is you can reverse the direction of the magnetic field here. For example, if you have a sinusoidal voltage here, you may have a positive voltage at one position, so it may have a current in one direction, but if you have a negative potential, it would draw current in the other direction. So you can change the direction of magnetic field in this configuration. You can't change the magnetic field direction in that direction unless you rotate the whole magnet. So in this case, just by placing these to each other and by changing this thing, without changing the distance, you can change the flux between that. So let's try to find out what would be the induced EMF in this case. So let's say this distance is distance z. What would be, so you have a current carrying loop, and this current carrying loop is carrying a certain current I1. What would be the magnetic field due to a current carrying loop along its axis at a certain distance d? We already know this problem. What would be that? The magnetic field due to the coil number 1 at a certain time t is given by, approximately given by mu0 by 4 pi 2 mu of the first coil divided by the distance z cube, where mu1 is the dipole moment of this coil, and we already know what's the dipole moment of a coil. It is given by current which is flowing that coil multiplied by the area of that coil. So let's say the area, the radius of this coil is r1. So that would be given by I1 of t multiplied by pi r1 squared. So you have this magnetic field given by 4 pi 2 into I1 of t pi r1 squared divided by z cube, where z is the distance between the two coils. So this would be the magnetic field magnitude at this location. And we are assuming that this magnetic field is not changing across this coil. So that's the assumption you are making. So what would be the total flux through magnetic flux through the second coil due to that magnetic field produced by the first coil? This would be equal to B field, which is B1 at T dotted with area dA over the surface S2, where the surface S2 is this surface enclosed by the loop. So that would be the magnetic flux to the second coil. And so for simplicity, I can assume that A and B are in the same direction. So B dot dA would just give you B dA. So what would be that thing then? That would be B1 as a function of time multiplied by the area of this S2. What is B1 of T? We already know it. That is mu0 by 4 pi 2 I1 of T pi r2 squared divided by z cube multiplied by the area So the area is pi so this is R1 squared. This is R1 squared multiplied by pi R2 squared. So this is the area of the first loop, because the area of the first loop gives you the magnetic moment of the first loop, and the magnetic moment of the first loop gives you the magnetic field which is created at the location of the second coil. And this area is coming from this thing, basically the magnetic flux through the second coil. So यहाँ पे जो area आएगा, that will be the area of the second coil, जिसकी through जो है वो flux जा रहा है. So that would be the multiply by, so that would be your flux, magnetic flux through the second coil. But because your current through the first coil has a time dependence, then you can find the time dependence of the total magnetic flux through the second coil, and that will be equal to mu naught by 4 pi 2 pi R1 squared pi R2 squared divided by Z cube into d by dt of I1 of t. So if you know the time dependence of this current, you know the time dependence of this current, you can take the derivative with respect to time of that current and multiply by this factor, and what you would get is the EMF which would be created inside the second coil due to a changing current in the first coil. The whole thing you can write is in this way. So your minus sign, so how do you find the minus sign? What does the minus sign indicate? The minus sign would indicate कि जो EMF की direction है वो क्या है आपके पास, and how do you find it? You just have to look at कि whether the flux is increasing through it or decreasing through it, and what's the direction of the magnetic field if it is increasing or decreasing, and that would give you the direction of that thing. So anyway, so जो आपके जो magnitude है, let's ignore the direction for the time, because the time is given by the length, the sign. The direction is given by the Lenz's law, so the magnitude of the EMF which is produced is given by this factor, and I would call this factor as M1, 2 multiplied by dI1 by dt. That quantity which I have represented by M1, 2, what does it include? It includes the area of the first coil, it includes the area of the second coil, and it includes the distance between the two coils. So what is this? It is basically a geometric factor which only tells you कि पहली coil का size क्या है, दूसरे coil का size क्या है, और दोनों के बीच distance क्या है. It has nothing to do with कितना current flow कर रहा है उसके अंदर. It's just a geometric factor. And this geometric factor is called as mutual inductance of two coils. It tells you कि अगर एक coil के अंदर आपके magnetic electric field change हो रहा है, current change हो रहा है, so how much current would you induce or how much EMF would you induce in the second coil? Of course, it depends on how much the current कितना fast change हो रहा है यहाँ पे. अगर fastly change होएगा तो यहाँ पे आपके पास जो EMF produce होएगा वो भी ज़्यादा होएगा, because it depends on di by dt. So अगर di by dt जो है वो आपके पास तेजी से, it's a high number. If it's a high number, it means कि जो induced EMF है यहाँ पे is also a high number. But apart from this, it depends on this geometric factor. तो अगर ये चीज़ आपके पास ज़्यादा है, it means कि जो EMF आप produce कर रहे हो, there's also a higher magnitude. It totally depends. It only depends on what? The sizes and the separation between the two coils. So
that way, even if relation to it doesn't fit in any factor, because you is correct, is correct, you have to feel the opinion.
So again, like whatever the case may be, हो सकता है कि इलेक्ट्रिक मैग्नेटिक फील्ड मेरे पास इस डायरेक्शन में हो, it can either increase in that direction or it can either decrease in direction. So I might have, let's say, जो यहाँ पे करंट फ्लो कर रहा है यहाँ के अंदर, because I have a sinusoidal, so जो करंट मेरे पास होएगा I1 current as a function of time, it would be a sinusoidal current. So let's look at the first cycle. First cycle में let's assume कि करंट आपके पास इस डायरेक्शन में फ्लो कर रहा है, तो अगर इस डायरेक्शन में फ्लो कर रहा है तो मैग्नेटिक फील्ड की ये वाली डायरेक्शन है, तो इस केस के अंदर, इस साइकिल के अंदर मैग्नेटिक फील्ड की ये डायरेक्शन होगी. ठीक, अब लेट्स लुक एट द फर्स्ट पार्ट ऑफ दिस साइकिल जिसमें ये करंट जो है वो इंक्रीज कर रहा है. तो अगर करंट इंक्रीज कर रहा है, so you have magnetic field in this direction which is increasing in time. तो जब इंक्रीज कर रहा है तो what you want कि आपका जो EMF क्रिएट होएगा वो ऑपोजिट डायरेक्शन में होएगा. बट इन द सेकंड साइकिल आपकी मैग्नेटिक फील्ड की डायरेक्शन स्टिल द सेम है, क्योंकि करंट अभी भी उसी डायरेक्शन में फ्लो कर रहा है, लेकिन वो करंट अब डिक्रीज होना शुरू हो गया है. सो जो बी फील्ड इस डायरेक्शन में है वो आगे पास डिक्रीज होने लगा है. तो अगर वो डिक्रीज होने लगा है तो EMF भी उसी डायरेक्शन में क्रिएट होएगा. सो you have to do it for each cycle. Similarly, यहाँ पे the case would be other way around. So you have to look at कि each cycle के अंदर क्या हो रहा है. So that's why I just put the magnitudes here, and I don't care about the direction for the time being. The direction you have to figure out with Lenz's law. And the Lenz's law would tell you कि minus dV by dt की क्या direction है. That would be the EMF direction. So if I put the direction in this whole thing, what I get is minus m12 di1 by dt, and this is my total expression for this. Minus take care of ये आपके पास okay. Okay, what if I increase the number of coils in here? What do you expect क्या होएगा? Let's say अगर मेरे पास यहाँ पे एक coil है, instead of one coil, I have two coils here. So let's say I have n2 number of coils. What would happen to EMF? Would it increase or would it decrease? You have two wires now which are feeling this changing flux, and you would have an induced EMF in each of those coils. So let's say in general, if you have n2 number of coils, when your total EMF produced होगा, that would be minus, you have to multiply by n2, because हर coil के अंदर एक अलग induced EMF होएगा, and if you add all of them up, you would get basically n2 multiplied by your whole EMF. Multiply by the number of true, you can say that. Similarly, you can include, what if you increase the coil number here? That would be again the same problem. So, अगर यहाँ पे आप क्या करते हो, coil number increase करते हो, so in this case I have, let's say, n1 number of coils. What I am doing here is जो magnetic, क्योंकि you have n number of coils, जो magnetic field produce होएगा यहाँ पे, वो आपके पास higher magnetic field produce होएगा. So यहाँ पे जो E field है, यहाँ जो flux है, वो आपके पास n1 से multiply होएगा. Sorry, n1 से. क्योंकि B field जो है वो n1 time is higher. Because you have n1 current, loop currents, not one loop current. So what you would have, m12 के अंदर you would have this n1 as well included. But normally the convention is कि जिस लूप के अंदर आप क्रिएट कर रहे हो, that would come out, but you can put that in as well. It's again a geometric factor. It is something which is constant. You are not changing with time the number of turns in either of the coil. So this is something which is constant in the problem, and this is not a time dependent thing. You can put both n1 and n2 in this m12. So I can write the whole thing again like this, but in this case m12 मेरे पास क्या होगा? That would be mu0 by 4 pi n1 N2 pi r1 squared pi r2 squared divided by z cube. तो अगर आप n1 को आप कांस्टेंट रखते हो n2 को आप इंक्रीज करते जाते हो, तो जो इंड्यूस्ड ईएमएफ होएगा आपके पास और जो बस ज्यादा होएगा. दैट्स व्हाट हैपेंस इन अ ट्रांसफार्मर. ठीक है. सो sometimes you don't want, so these are two independent circuits, and by changing in one circuit you are inducing current in another circuit. So if you have circuits which are, if you have a chip which has many circuits, so any change in one circuit would create current in another circuit. This is something which we would call as mutual inductance. So this might be not a good thing, because you don't want an inductance in a circuit due to a nearby circuit. So this may be a bad thing, but in other circumstances it can be a good thing. For example, that's what you want in a transformer, that you have one coil and you want to induce EMF in another coil. So that would be desirable in that case. So mutual inductance can be good, it can be bad depending on how you want to utilize this effect. Okay, one thing I would say is, normally जो N2 है वो उसमें included नहीं होता. So what you say कि आपके पास एक coil है जिसके अंदर current है, जिसका कोई area है, then you have another coil जिसके अपना area है, and so you have a mutual inductance, and so एक coil के अंदर कितना current induce होता है, so how much EMF would you induce in N2 number of coils? So normally N2 multiply होता है इधर, ये उसमें नहीं include होता. It's just a matter of convention. How do you like it? So, okay. So let's take a case of a transformer. So you might have seen transformers, something like this. So these are how the transformer looks like if you have seen one of those in the labs. So what you have is a coil or a solenoid or with which a certain time dependent current is entering and leaving it. So what you would have is a certain magnetic field which would be produced due to and that magnetic field would be a time dependent function. So why you have an iron core inside here? You have an iron core inside here. So what does an iron core does? You have so if you have just a simple solenoid, you might produce a magnetic field here which will be simply given by mu naught and I, or let's say this is Ni1. But if you have an iron inside this thing, let's say this, what would be the magnetic field which you would be producing in this case? That could be given by mu naught into 1 plus chi and I1. If you remember what he said, if it is a ferromagnetic material or any magnetic material, if you have any material, you inside the solenoid, you are increasing or decreasing the magnetic field. अगर पैरामैग्नेट है तो you are increasing the magnetic field. अगर diamagnet है तो chi m is minus, so you are decreasing the magnetic field. And if it is a ferromagnet, this chi, which is magnetic susceptibility, this is a very large number, so you are increasing your magnetic field by a large factor. So what you are doing by putting it in around such a ferromagnetic material is that you are increasing your magnetic field strength inside it. So if you increase this, you have another coil on the other hand side. So the flux, so you are increasing the magnetic field lines. So let's say your magnetic field strength is very high here. So the magnetic field lines which would come around, you would have a very high flux through this second coil. And if you have a high flux through the second coil, the change in the flux when this current changes would also be a stronger thing. So let's say if you are taking a flux here, and if this, so if the flux is changing with time through the second loop, and if this would be the case, where you don't have any magnetic material inside, this would be the case. But if you put a magnetic material inside, what happens is you have a very strong change in the flux through the second coil. So that's what basically this magnetic core gives you. क्योंकि it increases the magnetic field strength, और magnetic field strength increase होती है आपके पास, तो flux change increase होएगा. अगर flux increase होएगा, तो flux के अंदर जो change आएगा, वो भी increase होएगा. चेंज क्यों आता है आपके पास? क्योंकि यहाँ पे आपने you have put a sinusoidal source connected with the of course the resistor. So what you want is EMF. What does an EMF depend on? It depends on, in this case, the mutual inductance of the two coils multiplied by the di by dt, and the mutual inductance of another case d by dt of phi m, and phi m includes b dot a. तो अगर v dot a आपके पास ज़्यादा है, phi m ज़्यादा होएगा. अगर phi m ज़्यादा है, so the change in phi m is stronger as well. So that's what you want, कि अगर आपके पास higher EMF produce हो. But there's a problem here, and the problem is, let's say if you are increasing the current here. So if you are increasing the current, जो B field है इस direction में, वो क्या होएगा? That would increase. So you have a B field which is increasing. So you would have a non-Coulombic electric field which would form inside the solenoid. It can form outside the solenoid as well, but it can form inside the solenoid as well. So let's say the current increase कर रहा है आपके पास, induced EMF किस direction में produce होएगा? You have a current, you have a magnetic field in this direction which is increasing, so dB by dt is that direction, minus dB by dt in this direction, so जो induced EMF आपके पास create होएगा, वो आपके पास opposite direction में होएगा. So if you have that thing, तो जो आपके पास so and inside, so inside you have an induced EMF which is the other way around, and inside you have a material which is conducting as well. और वो क्या है? This is iron. So the iron है, you would have currents which would be running the other way around inside. Those currents they are called as eddy currents, and those are the currents which you don't want. For example, if you have a fastly changing, oscillating source, so you would have currents, so which would be oscillating back and forth, and the faster you want to change the current, the more you would have those eddy currents, and the more you do have the eddy current, it would heat up that transformer. And you don't want a heated up transformer. That's why if you have seen one of those big transformers, they are always kept in kind of a, they have these things around it which have oil inside, and that oil especially put inside to keep them cool all the time, just to get rid of those, so that the heating will produce the eddy current you are saying, you can get rid of it. But you can also, yes. So let's say अगर आपके पास changing electric field है या changing source है यहाँ पे, so it would increase the current or it would decrease the current in one direction or another. So let's say if it is increasing the current, it is increasing the electric flux through this surface. So the electric flux, so it would induce an EMF in the opposite direction by Lenz's law. And so you have a non-Coulombic electric field inside which is produced. इसकी वजह से अगर current produce होंगे, which would heat up. So that's why if you have seen those transformers, so they have something like this in there. Have you seen those transformers? They have some kind of lines around this. What are those things? They are basically you have conductive layer, then you have an insulating layer, then you have again a conducting layer and an insulating layer. So those are that thing. So if you look at a cross section, so what you have is, let's say if you have an eddy current which you want to avoid, so you put those insulator in between so that the eddy current can't flow freely enough. So they would be confined in those small spaces and they would become much weaker as a result of that. So that's why you have those kind of things in there. In which coil? Is coil के अंदर. So your direction, okay, it would depend on कि यहाँ पे आप कौन सी cycle के अंदर हो. ठीक है? If you are in the up cycle or on the down cycle and on which quarter of the cycle, so it would determine. So let's say अगर आप इस cycle के अंदर हो जिसमें आपके पास magnetic current increase कर रहा है, ठीक है? Current increase कर रहा है तो flux through it would increase, flux through it would increase, so you would have a current which would be in the opposite direction. And you can increase or decrease the total EMF which you produce here by just changing the number of coils. So अगर आप N2 को आप increase करते हो, तो जो EMF magnitude आप create कर रहे हो, you are increasing it or decreasing it relative to the first coil numbers. So that's what this mutual inductance is. So just the last thing, let's say if I have a solenoid and I don't have any other coil nearby, but what do I have is a sinusoidal field which is current which is passing through it. So if it means that you have what would happen to this magnetic field which would be here? So it would be switching direction in each cycle. Maybe in this direction one cycle, other direction one cycle, and its magnitude would be oscillating all the time as well. So what you have is, you can consider the same coil. The same coil के अंदर आपके पास flux through it is changing. If the flux through the same coil is changing, you can have induced EMF in the same solenoid itself. This is something which is called a self-inductance. So if you try to increase or ramp up the current through a solenoid, because the flux through a solenoid would increase, so it would induce an EMF of its own to oppose that increase. So you would have an opposite current which would be start. It would try to minimize the current increase. So that's the self-inductance of the same solenoid acting on itself. So that would be something we'll be taking up next time.